Our next presentation is entitled Evaluation of High-Oleic Peanut Germination on Thermogradient Table, and our presenter is Nick Hurdle.
Well, thank you for that introduction, Dr. Kimwright. And as he said, my name is Nick Hurdle, and I'd like to discuss with you all today the evaluation of high-oleic peanut on a thermogradient table. First, we'll briefly discuss the four market peanut types. There are runners, which exhibit a prostrate growth habit, that exhibit indeterminate flowering along with a uniform kernel size, and make up about 80% of the United States peanut production. Next, there are Valencias, which exhibit an erect growth habit and flower along the main stem and lateral branches. There are also Spanish, which also exhibit an erect growth habit and flower along the main stem as well as the lateral branches. And finally, there are Virginias, which exhibit a bunch growth habit and do not flower on the main stem and make up about 15% of the United States peanut production. So what exactly is oleic acid? Oleic acid is classified as a monounsaturated fatty acid containing 18 carbons and one double bond as indicated on the picture on the right. Within a standard peanut, there is about 45% oleic acid and about 35% linoleic acid. Within a high oleic peanut, there's approximately 80% oleic acid to only 2 to 3% linoleic acid. So why exactly do you want a high oleic peanut? A high oleic content will equal a longer shelf life. The oxidative stability index has about a 7x increase compared to a low oleic peanut, and the oxidative stability index predicts the relative oil shelf life. There are also numerous health benefits, such as reducing the LDL cholesterol or the bad cholesterol, as well as raising the HDL or good cholesterol. But it can also reduce the systolic blood pressure and reduce triglyceride and blood glucose levels. There have been several studies looking at the interactions between temperature and high oleic content. One study noted that there was a reduction in germination at cooler temperatures. These investigators used a Virginia type with 12 cultivars with 6 low oleic and 6 high oleics. The standard germination temperature was at 30 degrees and 20 degrees Celsius with 16 hours at 20 degrees Celsius. The cool germination was at 18 degrees Celsius. These investigators noted that all HO seed had lower germination when compared to a low oleic cultivar by about 2 to 15%. A similar study was performed using the Spanish type peanut with 4 low oleic, 3 medium oleic, and 3 high oleic varieties. These investigators also noted that as temperature decreased, so did the germination in all HO varieties. It was also noted that one HO variety was consistently lower than all other varieties across all temperatures. So how exactly are these HO lines developed? The ones that we use for our study are considered near-isogenic, meaning that the breeders took a trait donor and they bred it with a recurrent parent to create the F1 generation. They took this F1 generation and bred it back with the recurrent parent several times to create the BC6 generation, which is about 99.2% of the parent germplasm while still carrying that HO trait. But growers are still very hesitant to plant these HO lines as there is a lack of agronomic information about them. So the objective of our study was to determine the germination rate of high oleic and low oleic cultivars across multiple temperatures on a thermogradient table. And our hypothesis for the study is that the oleic acid will not affect peanut germination. We used seed harvested in 2017 and 2018. For the low oleic varieties, for runners, we used Tifguard. For Virginia, we used Bailey. Valencia, we used New Mexico Valencia A. And for the Spanish, we used RSOC S140-1. For the near-isogenic lines or the HO lines, for runners, we used 62-15. Virginia, we used Bailey 2. Valencias, we used New Mexico 308-2. And finally, for Spanish, we used Oleic. This test was conducted in 4 states with seed grown in Georgia, New Mexico, North Carolina, as well as Oklahoma. We had 3 reps per cultivar per state. We then placed 20 seed per petri dish as shown on the pictures on the right, and each seed was treated with Rancona VPD. We then added water according to which side of the table the dishes were on and maintained appropriate moisture throughout the entire study. So a little bit more about our thermogradient table. It is pictured on the right. It measures 24 cells by 9 cells long, totaling 216 cells. It weighs approximately 1,000 kilograms for temperature control. We subjected the seed to a wide temperature range of 11 to 33 degrees Celsius. We also maintain this temperature using a 1:10 ratio of ethylene glycol to water. We placed a thermocouple at each cell for temperature recording, and the GDDs were calculated from the high and low temperatures for each cell across the entire study. We collected data daily from day 3 through day 7. We collected the number of germinated seed, and to be classified as germinated, the radicle must have been at least 5 millimeters in length. Once a seed was classified as germinated, it was removed from the table. For our analysis, we wanted to determine the GDDs needed for 80% germination, so we used the nonlinear model below to establish the parameter estimates that B0 is the upper asymptote, B1 is the relative slope, XP is a value of X or the number of GDDs when Y is at P% of the upper asymptote, and again we used 80% for this study, and Y is the percent germination data. We then graphed it in SigmaPlot 14 with a separate curve fit for each cultivar and oleic content, and it is worthy to note that the data was combined across location for each year. We then utilized PROC NLN in SAS University to establish the confidence intervals, which were then used to indicate differences within the high oleic and low oleic cultivars. We used the cumulative germination at 168 hours after initiation, so the germination of the 24 cells were averaged. So let's move into our results. First, we'll talk about the 2017 harvested seed. Along the x-axis is the grown degree days, and along the y-axis is the cumulative germination. It is worthy to note that the solid line represents the HO, or the near-isogenic lines, while the dashed line represents the parent lines. The red are the Virginias, blue are the Spanish, black are the runners, and green is finally the Spanish. In 2017, this graph indicates to us that all parent lines for all cultivars reached 80% germination faster than their near-isogenic lines. This was also noted in 2018, in which the parent lines all reached 80% germination faster than the near-isogenic lines, except for the runners, which were nearly the same. Next, let's move into our parameter estimates. Again, B0 is the upper asymptote, B1 is the relative slope, XP is the value of X when Y is at 80%, and also the parameter estimates followed by the same letter within HO and parent cultivars are not different. So for B0, the upper asymptote, the HO lines and parents were different for all cultivars except the runners, in which they were the same. For the B1 slope, the parent New Mexico Val A for the Valencias was lower than the slope for the Valencias. And finally, for the number of GDDs needed for 80% germination, there were no differences noted for any of the cultivars. In 2018, for the upper asymptote or maximum germination, the only difference was with the Spanish, in which the parent RSOC S140-1 had a higher percent germination compared to the High-Oleic line. For the slope, there were no differences indicated. And finally, for the value of X or the GDDs needed for 80% germination, the only differences were noted was with the Valencias, in which the parent New Mexico Valencia A line needed fewer GDDs when compared to the HO New Mexico 308-2 line, also indicated by this graph. So let's talk about the percent germination in 2017. All seed reached at least 58% germination. with an N of 5,760 seed per cultivar. In 2018, all seed reached at least 64% germination with an N of 4,320 seed per cultivar. When we compare the germination rates between 2017 and 2018, they are very similar to each other, indicating to us that the HO lines are genotypically stable. So in conclusion, for 2017, all parent varieties had a higher germination except for the runners. And the 62-15 and the RSOC S140-1 needed the fewest GDDs at only 27.4 to reach 80% germination, while the Virginia High-Oleic line Bailey 2 needed the most GDDs at 34.2. In 2018, the RSOC S140-1 total germination was higher than the HO line Oleic, and the New Mexico Valencia A needed only 11.2 GDDs for 80% germination. So we will reject the hypothesis due to the parent lines having a higher germination than the HO lines. The HOs typically needed more GDDs for 80% germination, and the lower GDDs needed for 80% germination indicate a higher seed vigor. So for future research, we are currently analyzing the 2019 harvested seed. I'd like to see this test performed on newly developed HO varieties, as well as possibly extending this test from 7 days and terminating it at 10 days. I would first like to thank the Georgia Peanut Commission, as well as the peanut breeders from New Mexico State and Dr. Popala, Dr. Holbrook from the USDA in Georgia, from North Carolina State, Dr. Eastland and Dr. Dunn, as well as Dr. Chamberlain from the USDA in Oklahoma. I'd also like to thank Dr. Lisa Dean for the seed oleic acid testing, as well as Mr. Sidney Crone for his technical support. Finally, I'd like to thank the UGA student workers of Owen Kimbrell, Sammy Bowen, as well as Colby Lynn for their support throughout this study. And here is a list of citations used throughout this presentation. And with any remaining time, I'd like to answer any questions that you may have.
Thank you for that. We have a couple questions for you.
Mm-hmm.
First question's coming from Dr. Kelly Chamberlain. And how can producers and the peanut industry use this information to benefit their production strategies?
So the question is how can growers and the peanut industry use this information to better? Well, since we did see a lag in the HO lines early on in the test, I would recommend to growers that to not exactly think about replanting early on, to give them a few more days to allow them to germinate, which is again why I wanted to extend this test to 10 days after instead of 7. So I would recommend to growers to tell them you may not be seeing early season germination, give it a few more days and they should pop up. And if they don't, for whatever reason, then consider replant or different options, but give them a few days for the HOs to germinate.
Second question comes from Dr. Barry Tillman. Do you have a biochemical hypothesis for why the high-oleic acid might reduce germination?
So the question is, do I have a biochemical hypothesis as to why the HOs did not germinate, as well as the parent lines? I actually do not, but they may not be as efficient in the biochemical processes as the parent lines. That is one hypothesis, but I'm not exactly sure.
Okay, thank you. Next one is from Dr. Dylan Wan. Any thoughts on what physiological mechanisms in the high-oleic, this may be a similar question, any thoughts on what physiological mechanisms high-oleic lines are slowing germination? I think you've answered that. Any further thoughts on that?
No, they may be different, may be more efficient at the biological processes. I'm not exactly sure.
Okay, and one final question from Jack Davis. Was there any control for seed maturity in this study?
So the question is, was there any control in the seed maturity of this? These seeds were grown under normal agronomic practices for their respective regions and states. Okay.
All right, that concludes the time we have for your presentation. Thank you very much.
Thank you.